5.
In 1977, the greatest adventure in space exploration commenced.
We have ignition, and we have liftoff.
Our eyes, our minds, our souls are moving out through the universe.
You can only do things for the first time once. And Voyager kept doing things for the first time over and over again.
2 robots were built to be able to think and explore by themselves in the deep reaches of our solar system.
None of the managers really appreciated the complexity and the autonomy that we just launched into space.
Yet both missions went seriously wrong only moments after taking flight.
We thought that we'd lost the spacecraft.
They went on to make astounding and unexpected discoveries.
When you see things that you did not predict, that's when there's the most to learn.
"40 years ago, the greatest adventure in space exploration began with the launch of the Voyagers. And we're here today to remember, to celebrate, and to find out what these magnificent machines are still doing. I want to introduce our panelists, but if you will, please hold your applause to the end. First is Susie Dodd. Susie's first job out of college was to work on Voyager. She went on to become the project manager of Voyager and had that top job when Voyager 1 became the first spacecraft ever to reach interstellar space. Chris Jones is JPL's chief engineer. He helped to bring the Voyagers into being. And these days, he's still providing advice and guidance on how to keep them working. Chris played a very important role in the saving of Voyager 2, and we'll hear about that in a minute. John Cassani. John is one of the great pioneers in space exploration. He arrived at JPL in the 1950s. And if you're a fan of the gold record, you have John to thank. And Dr. Ed Stone, professor of physics at Caltech. He served as director of JPL from 1991 to 2001. And in 1972, he was named the project scientist for Voyager. It is a position he has held for 45 years. The one and the only project scientist that Voyager has ever known. Will you please give a very warm welcome to our panelists. Now, there are other members of the Voyager team who are here. Some that are still working in the lab, some who've made special effort to be here today. And we would be amiss without acknowledging their contributions to this mission. So would you please, everyone who's ever worked on Voyager, would you please stand so we could recognize you? Yeah. There are a lot of reasons why Voyager is so extraordinary and special, but one has to do with the alignment of the planets. And I was wondering, Ed, if you could tell us what that was all about.
Well, there was a graduate student from Caltech who was up at JPL summer of 1965, and he'd been given the task of looking for opportunities to fly by Jupiter as a way to speed things up in the outer solar system. So these are gravity assist flybys, and in that process, he discovered that if you launched a spacecraft in 1977 or 76 or 78, the planets, Jupiter, Saturn, Uranus, and Neptune, were all lined up so that with one assist after the other, one could speed the journey out to Neptune, normally 30 years down to 12 years. And this soon was called the Grand Tour and led to what eventually became Voyager 1 and 2.
So when this opportunity was there, were we ready, John? We've never been to the outer planets. We hadn't been any further than Mars, right?
That's right. We've been as far as Mars is as far as we've been. So it was quite a challenge. I mean, NASA had funded us an advanced technology development program to explore, develop some of the new technologies that we thought we were going to need. The problem was time. We had never developed anything reliably that would last beyond Mars. You know, and nobody had really flown anything beyond Mars before that. And so I think that's what occupied our concern for the most part. I mean, we built a lot of Mariner spacecraft, and the Mariner family had really had a long series of success. But those were Venus and Mars missions, and we were going to take on something that was not going to take 2 years or 3 years. It was going to take 12 or 30 years. And we're talking about the Grand Tour, but even when it was cut back to just Jupiter and Saturn, it was still 10 or 12 years, and that was kind of scary.
And you were funded just for going to the first two of the outer planets, and you somehow worked it out so that it was possibility to go further, correct?
Well,
you can tell it now, John. It's okay.
Well, we were not supposed to work on anything further than Saturn, and that was a pretty strict direction that we had from headquarters. And I wasn't the first project manager. The first project manager was Bud Schermeyer. Okay. And when NASA decided not to go forward with the Grand Tour, it was Schermeyer who led the charge with an idea. Look, we don't have to do all 4 of those planets. Let's just cut it back to 2, and it'll take a less aggressive approach to the technology. We won't have to use so much new stuff, and we can capitalize on the Mariner brand name, because Mariner, we had a string of 10 or 11 successful Mariner missions. And so that sounded like a good idea, and headquarters went for it, and we got started. I guess it was 72 was the official go-ahead for that.
Yeah, I think that one interesting thing that is not generally realized is when Mariner, Jupiter, Saturn, 77 is what it was called. It was a 4-year mission, and success was one of 2, at least one, of actually getting all the way out to Saturn. And it turned out that in those days, a fiscal year ended in June. And so the mission had to end in June of '81. And that meant that the aim point to go onto Uranus was inside the rings. So in fact, until about 75 or 76, when Voyager was then approved to move the aim point further away, and that's the reason we arrived later than June. We arrived in August. That was outside the rings, and in fact could go on to Uranus and Neptune.
So that was completely financially driven?
It was driven by the fact the fiscal year ended on June 30, and they wanted the mission over by June 30.
Yeah. I didn't know that.
Okay, all right.
They were afraid of some project scientist would make a career out of it.
All right, well, let's move ahead to the launch period. John, I understand you made the decision to launch the first one and call it Voyager 2, which confused all of my brethren in the press as to why you would launch Voyager 2, but it got even more complicated during the actual launch. So let's see what happened during these launches.
5, 4, 3, 2, 1. We have ignition, and we have liftoff. We have liftoff of the Titan Centaur, carrying the first of 2 Voyager spacecraft to extend man's senses farther into the solar system than ever before.
Voyager's programmers had taught the spacecraft that if it sensed anything unusual, to switch to backup systems. And that's exactly what had already occurred. Engineers call this fault protection.
The fault protection started doing its thing, reconfiguring the system. We're still attached to the launch vehicle. It's in the early stages of its flight, and the first thing we see are the gyros being swapped.
The launch vehicle, as part of its powered flight, went through a roll. And the spacecraft would never have done that on its own, so the spacecraft thought that was a fault.
I think there were 6 or 7 different states that it went through in trying to correct the fault. Well, soon I can't have 2 gyros fall. Must be a computer that has failed. It switched out. We had redundant computers, so it switched out computers. Well, it can't have been that. It must have been something else. So it went through this whole sequence of trying things, and we thought, holy mackerel, this spacecraft looks like it's gone bonkers. And we thought that we'd lost the spacecraft.
Finally, we got to separate from the launch vehicle and we were on our own, but the problems weren't over.
The spacecraft was now slowly tumbling.
Chris, help.
Do you realize how tired I am of giving this talk?
I don't care. Want to hear?
Okay, so there's a long version and a short version. I kind of like the way Kasani set up the pace of this. There were a couple of gyro swaps while we were still on the launch vehicle. Oh yeah, there's that picture.
There you are, right there in the middle.
And fault protection was fairly quiet up till that point. We did the injection burn with the propulsion module. That was just right on, separated from the propulsion module, and we experienced high rates, high tip-off rates. And so we ended up switching thrusters. And so 4 thruster swaps, 2 high-bix swaps, and a processor swap later, all within 14 seconds, something like that. Was a very active time for the fault protection. We'd never done anything like that in test. It was a very good stress test for the vehicle, but it wasn't what we were looking for. And so finally, the thing that saved the day was that processor swap, because that brought online a fresh software load, set as though it were for launch. All the errors, accrued errors are 0. And so it was like giving the spacecraft a second chance. And then just wait for the craft to recover, and recover it did. We got to a point where all the commands, all the coded commands in the sequence had executed, but we were not pointed at the sun. And so the spacecraft automatically initiated a sun search command, and we began turning in an effort to catch the sun. A thermal guy once told me, he says, when in doubt, keep moving, and that's really what you need to do near Earth. And so we got through the first turn, no sun. We got through the second turn, no sun, and then partway through the third turn, we saw the sun in the sun sensor field of view, and the rest was easy.
Yeah, well, one of the hard parts of this, though, is the fact that there was a question of whether to reset, and the cool guy who said just let it go was this man here who saved.
You're too modest.
Yeah,
Chris.
saved the mission.
He did.
Yeah.
And just imagine how it would have been differently. All right, well, we have to get on because we haven't even gotten out of Earth orbit yet.
Well, that was just a short version.
And just to say that the second launch had its problems also, and fortunately the computer was able to recalculate, and just a few seconds of fuel left, I think, at the very end.
The Centaur guidance.
Yes, no problem with JPL engineering on that one. No, whatsoever.
That was good, though.
Yeah. So,
by the way, there was no problem with JPL engineering on the fault protection either.
well noted. Just well noted.
For those of people who might have seen the Farthers film, there's a little bit with Charlie and me in it in the Black House on the second launch. But they all depend.
Charlie Cohase, who's very much involved, a genius of navigation on Voyager throughout its mission.
Right. Yeah.
Great job.
Charlie is sitting in front of a console, and I'm sitting next to him, and he's over to me. He says, "John, He says, this isn't looking good. I said, what's the problem? He says, I don't think we're going to achieve the velocity that's required. And then we said, we didn't know why or anything, but it was pretty clear at the end of the second stage burn that we hadn't made it. But the system was being guided by the Centaur guidance system, and the Centaur guidance system knew that there had been a deficit of velocity, and it just kept the Centaur engines burning a little longer, and we made up for it. But that was amazing. And what happened? There was a leak in the propellant line, and propellant was being spewed overboard. It didn't cause a fire anywhere it wasn't supposed to, but that's another story.
So as Voyager 1 was leaving, it took this amazing picture. We'll show you. Very historic. First time that we saw the Earth and the Moon together. But let's get on to our first planet encounter. So if we can roll that video, let's go to Jupiter.
For 7 years we'd been preparing, and suddenly for a period of several months we were overwhelmed with a flood of discoveries, one after the other, many every day. One of the challenges we had in planning, because all this has to be pre-planned and all has to be loaded onto the spacecraft and then executed automatically. What do we look at? When? What do we observe at what time?
Stone knew that taking the position would mean coping with sizable squabbles among a science team numbering over 200.
I think the point is that we don't want to work the problem here. If there are some problems, there's an outside forum to do it. Let's. Sure.
It was a great training ground for learning how to handle conflicting science requirements. There's a phrase that shows up in discussing science conflicts. My science is better than your science. And if that's your only argument, you're not going to win. You've got to convince the other guys that you've got a point that your science is worth doing and it's worth trying to accommodate it.
I remember being in the ops center at the first Jupiter encounter and seeing these pictures returned in real time, an image every 42 seconds, downlink from the spacecraft, at these odd-looking worlds. Just blew us away. And I really experienced the sense of discovery.
As we approached Io, we saw an object that looked unlike anything we'd ever seen before. In fact, we have not seen anything like it since. We did not understand what we were looking at all. It was so different than anything we had imagined. And it was only as we were flying by Io that a navigation image was taken, that is, an image taken with a deep exposure to find the stars in the background, that a navigation engineer, Linda Morabito, noticed that there was this large plume off the limb of this little moon of Jupiter.
The phantom moon turned out to be a gigantic plume of gas and dust, shooting skyward from a volcano.
And that was the first indication that this is the most volcanically active body in the solar system, 100 times more volcanic activity than Earth. And yet it's just a small moon orbiting this giant planet.
All told, the two Voyagers took more than 33,000 images of Jupiter and its major moons. What these images and the other science results revealed was an exotic system that was not only vast, but beautiful, and almost beyond imagining.
It still takes your breath away a bit, doesn't it? So Ed, two questions for you about this encounter. One is, nothing like this has really happened with scientists before, where this coming down so quickly and the press is, and the public is wanting you to say, what is it? And this whole notion of instant science that you were so involved in. Can you talk about the decision you made to do that? That was sort of a risk in another way, wasn't it?
Yeah, this all began when I was up at Ames for the Pioneer 10 encounter with Jupiter, and I walked into an auditorium full of reporters wanting to know what was happening, what was being discovered. I realized we had a wonderful opportunity to communicate, but if we had to prepare for those interactions so the press could really tell the story. And so we set up a schedule of science discussions in the afternoon, getting ready for the press conference the next morning. That afternoon, more science for the next press conference the next morning. And it was a way of doing peer review so that, in fact, there was some assurance that we were not talking nonsense. But when you see things like 8 volcanoes, that's a pretty exciting discovery, of course, but since nobody had really suggested that kind of volcanic activity, 10 times that of Earth. Yeah, it was this instant science was always a challenge because scientists really are used to having peer review, and these afternoon science discussions were our form of peer review, deciding what's ready for the press the next morning. Now, at that time, to get ready for the next morning, you had to send material out for preparation. The imaging team had to choose which images. They had to write the captions, prepare them for the press.
Have them printed.
Have them printed.
No digital then.
No digital. If you wanted a picture from Voyager, you had to be here collecting it. There was no internet. There was none of that. It was all, you had to be here. So people who were here really were very advantaged. Today, everybody can be there, but in those days, only a limited number of people could have the sense of discovery that we all enjoyed day after day after day.
And you know, you sort of have this theme that gets set at Jupiter that we'll, as we go through, we're going to see through the whole journey through the outer planets of being geologically alive and the moons being so important.
Of course, the moons before Voyager were just literally points of light. But we had some idea of color because that you could get from a point of light, but other than that, we had little to know about what these worlds are like, and it turns out they're diverse, they're distinct bodies. They could have all been heavily cratered ancient surfaces. I think very few such surfaces have been found in the solar system. It's a very active place out there today.
Let's go to Saturn.
As Voyager 1 bore down on Saturn, the spacecraft was clocking nearly 1 million miles a day. And each day, Saturn revealed itself in some new way.
This faint one, this faint one.
Among the tremendous surprises there was that we could be, still more than 1 million kilometers away, and we could see structure in the rings.
All right, look at that.
More and more, the rings were revealing their intricate and baffling structures. For many scientists, the moon Titan was as important as Saturn itself. Titan is so large that if it orbited the Sun rather than Saturn, it would be called a planet. It was already known that this was the only moon in the solar system having a substantial atmosphere. This might be a place, some scientists theorized, that resembled the Earth before life arose. And that made this moon an irresistible target. But getting the best possible views came with a steep price. It required Voyager 1's tour of the planets to end at Saturn. That was the choice made, for Titan was deemed that important.
There was this great hope that we'd be seeing down to the surface through this thick atmosphere, and we would discover, amazing things. As we got closer, at the time when we should have started to see features and resolution, it was awfully blank.
Although the hazy images of Titan were disappointing, the atmosphere was found to be, like our planet, rich in nitrogen. As hoped, this was in some ways a primordial Earth. After Titan, Voyager 1 swept underneath Saturn and then rose up out of the plane of the ecliptic and headed up towards interstellar space.
To look at that and realize that you're a spacecraft, you're basically saying, you must have felt like you were saying goodbye to it at that point. You didn't know how long it would last, and you built this thing, and bye-bye after Titan. Was that tough on you as an engineer or as a scientist?
I think you took a heck about that.
Actually, of course, this was just the beginning of the interstellar mission. In fact, when we finished Saturn, before Saturn, it was called the Jupiter-Saturn-Titan mission. And for Voyager 2 was the Jupiter-Saturn-X mission, JSX, Jupiter-Saturn-X, where X was either Uranus or Titan again. If Voyager 1 had not flown by Titan and gotten the data, Voyager 2 would have done the same thing and ended up going up out of the plane of the ecliptic and no more planets. So in that sense, Voyager 1 did its job for Voyager 2.
Would you have done that even if with Voyager 1 you didn't get exactly what you wanted and you felt like you needed to go back?
I think we would not have done that. But if Voyager 1 had not worked, in fact, NASA said, this is a mission to Saturn. You need to do a Saturn mission. And if you want to do Titan, which is clearly a very important thing to do, you end up out of the plane of the ecliptic.
That was a clear guidance from headquarters. And Bud Schermeyer, who was the first project manager, was very, very firm on us observing that. We were not to look at anything beyond Saturn. This was a Saturn mission, focus on Saturn, and the primary objective at Saturn was Titan. And if we did not achieve all of the Titan objectives, is the way I remember, we were going to send its twin spacecraft, Voyager 2, right back. That was the plan.
We had targeted Voyager 1 and Voyager 2 differently at Saturn because a single spacecraft can fly by close to only 1 or 2 of the moons. You can't get all 4. So what we purposely did was to focus Voyager 2 on Europa, which was the only one of the 4 moons that we had not gotten up close. And of course, what we discovered was it looked like a cracked, icy surface on a liquid water ocean. That's what it looked like. And with no mountains and no valleys. And just these cracks where stuff had come out on the surface of the ice.
It told me it looked like the cue ball he used to play pool with in Caltech.
So, of course, we've had fire, now we have ice. Yes. All this variation going on. Now, we're about to go to Uranus, and Susie, this is where you come into the picture.
Yeah, yeah.
You know, you were just getting out of college.
Right, the little college down the street there in Pasadena. I went to Caltech, so it was close by. And matter of fact, I found out about the job at JPL from being on campus, and people that know me know I do a lot of swimming. Person in the lane next to me said, "Hey, I hear about this job at JPL," and it's great. It's been fabulous.
Well, let's go and relive that experience at Uranus now.
After triumphs at Jupiter and Saturn, Voyager 2 was closing in on the first encounter ever with the ice giant planet Uranus. Voyager's journey to this point had taken over 8 years. And the wear and tear of 1 billion miles was beginning to show. The scan platform that moved Voyager's camera was prone to seizing up. Transmitting instructions to the spacecraft was an elaborate chore, as the primary receiver was no longer functioning and the backup was only partially working. Getting a signal back from Voyager was a challenge too. One-way transmission time now took 3 hours.
The extension of the mission to Uranus and Neptune, I think, highlights really one of the unsung heroes of JPL, and that is the Deep Space Network.
The Deep Space Network is a group of antennas arrayed in 3 strategic locations around the globe. This is the essential link for tracking and communicating with all of NASA's interplanetary spacecraft.
Those encounters at Uranus and Neptune would have been impossible without what the Deep Space Network, the DSN, did to get that data back. When you think about it, you've got the Voyager radio transmitter powered at about 23 watts, which is about the power of your refrigerator light bulb. And we're trying to pick up that signal here on Earth from well over 1 billion miles away. And picking out that very tiny little signal from that vast background of outer space is really a remarkable achievement when you think about it.
Uranus was a real planning challenge, and the reason why is, 1, we only get 1 shot, and 2, Uranus is kind of turned up on its edge. And we're now, instead of seeing the moons in kind of a plane where you can fly through this plane and get one after the other, we're looking at a bullseye.
That meant that the flyby of Uranus and its moons and rings would occur nearly simultaneously. Coping with so much to see in such a short period of time would make this the most intense of all the Voyager encounters.
You're given this pulse of data no one's ever seen, and you get it all at once. You get high resolution, comes up very, very quickly because these moons are small and you're flying by it at large velocity. So in a blink of an eye, basically you go from a very low resolution image to in-your-face high resolution and then gone again.
The initial calculations showed that we were going to be in great danger of getting really fuzzy pictures of practically everything if we didn't do something. And so we actually did some re-engineering on the spacecraft with the help of the engineering teams. We called it our anti-smear campaign. We basically improved our camera platform in flight by remotely changing how we operated it.
Well, Susie, it starts off that segment talking about this unsung hero of the Deep Space Network. You now are the director of the Deep Space Network, and why don't you tell us why it was such an unsung hero?
I think, you know, any mission, deep space mission, depends on the Deep Space Network. And the Deep Space Network started approximately in the early 60s, and as Ed likes to say, Voyager and the DSN grew up together. There were a lot of enhancements made to the Deep Space Network, particularly for Voyager. One of the enhancements was being able to array antennas on the ground for the Uranus downlink. And between the Uranus and Neptune counter, we increased the size of the 64-meter antennas to 70 meters. Just particularly for Voyager, as well as at Neptune in particular, we had to array other assets besides the Deep Space Network. The very large array we arrayed into the Deep Space Network to get the data back. And you know, the DSN folks are very dedicated to what they do. They are the unsung heroes. You would get zero data back from any mission from Mars and beyond without the Deep Space Network. And honestly, they're sort of happy to sit in the background and just be part of the crowd, so to speak. But it's a very important function, and we wouldn't have the data we have today without the antennas.
And Chris, we're now at the point where Voyager 2 is aging, and I think it's arthritic with an arm, and it's a little hard of hearing, or a lot of hard of hearing. Can you talk about some of the engineering challenges that you have with the spacecraft at this point?
Well, I mean, one thing you notice right away is that there's very little redundancy left.
Today there is like zero redundancy on either spacecraft.
That's right. That's right.
Yeah.
And the problem that gives you is that you still have people on the team who want to figure out some way to use the equipment that we have, even if it fails. You know, is there a way we can go through some back door and find another function that we can use instead? Those things don't exist really, but it keeps the team sharp, and it makes them think of other creative ideas to make the mission that we have ahead of us still a very meaningful mission.
I think it's really spectacular too when you think about it. There's two spacecraft that are still operating, not just one, but two that have gone from a 4-year mission to a 4-decade mission. And that's really remarkable. And I've read a lot on the history of Voyager, and picking up on something that John said, you know, it was designed as a 4-year mission. The engineers, or let's just put it this way, the managers were told not to think beyond 4 years. The engineers all thought beyond 4 years. When you look at the history of it, they'll say, well, I had a choice between part A and part B. Part B was going to last me longer. I chose that part. I didn't tell my boss. You know, I wanted to make it as robust as possible. And It's true, and I think the bosses kind of looked a different way. As long as it didn't, affect the budget too much, the boss looked the other way, and Voyager was built as robustly as possible.
Well, you're absolutely right about that. I was the manager of Division 34 before I went over to Voyager. And what I told the people in Division 34 was, look, we ought to be very, very sure that we don't build anything into this spacecraft design-wise that's going to limit its life other than the expendables. And we made some design changes that I never told Sturmeyer about along those lines.
Well, one of those was a sun sensor.
One of
the
them was
sun
a sun
sensor at Saturn, you're down a factor of 100. You could design it for that, and as soon as you go beyond Saturn, guess what? You couldn't see the sun anymore. So in fact, they put in an op-amp in to increase the gain so that in fact, now we're over almost 140 astronomical years away, and it still knows where the sun is.
So I think there's so much foresight given by the part of the engineers and the scientists to say, we want to make this an interstellar mission. As John said, don't do anything that screws that up, and do what's ever in your power to make this mission last as long as possible.
Susie, I want to ask you about, as engineering, what can you learn from Voyager that for these young engineers here, who may not have even weren't born?
Yeah, I always like to ask, how, is a show of hands of people that are actually 40 or under, if you want to admit it? All right, hey, very good. I like to, that's great, that's great.
So, let's take a moment here and just see if we can impart some wisdom.
I will add my 2 cents. I'll ask Chris to add his in a minute, because Chris designed it and he's now come back to help us work through the next 10 years of the mission, let's say. But I have 2 takeaways. The first one I kind of mentioned was the fact that the engineers designed it to be as robust as possible. I think you can take that away for any mission you're building. But do your best job and build in the robustness to make those rovers last more than 90 days, or last more than 2 years, or whatever mission you're working on. Secondly, document what you do. This is where Chris can chime in. As we are into the 41st year of the Voyager mission, we are trying to go back and look at why decisions were made on fault protection or designs in the software and things like that. And oftentimes you can actually find the decision, but you can't find any of the discussion of why the decision was made. And when I go back and ask, Chris, what did you mean when you wrote this memo in 1982? And he's like, let me go see what I can find in a box that I've sent out to archives.
At least I documented.
Yeah. In the fury of getting ready to get a mission launched, you're designing things. Keep a record of what you designed, keep the rationale, keep those notebooks. Ed Stone can go in his office and pull out a notebook from 1979 and go to the exact page he needs to go to find an answer. I don't know how many of you could do that. So it's important to document the rationale for decisions, and it will help the people who fly the mission. And if you're a person that generally just builds spacecraft and then goes to the next thing you're building and you're not involved in the operations, it's key for you to pass on that development knowledge to the operations people. Your success as a developer depends on the success of the mission getting the science back, and so you need to help the operations folks by doing due diligence in the development phase.
When we take on a new task, and I did some things that I never told John about,
They used to work for me. They knew better.
to move the state of the art forward, to improve the systems that we build so that they can get the best science, not just the required science, but the best science. That there's some things we could be doing that make a lot of sense. I'm not telling you not to tell your boss, but I think there's a lot of capability here that doesn't get exercised because we limit ourselves to what the what the last system looked like.
Okay. All right. They like that.
I guess.
Anything from the science side for young scientists?
Well, I think the interesting thing JPL does is missions that go where nothing's been before, do things that haven't been done before. That's what science is all about, is observing nature and understanding nature. And I think that's and what's required is an investment. In the case of Voyager, we spent 5 years from start of the project to launch, and no science for 5 years, but getting ready. And then when we finally got there in 1979, it was just lots and lots of science, exciting, but you have to be patient. It doesn't happen quickly, but you have to be patient.
All right, well, I think our spacecraft, Voyager 2, is on its way now to Neptune, and let's see if we can go there and see what happened.
The scientists knew that this was an epoch-making experience. Their knowledge of our solar system was advancing so quickly just because of these encounters. And I think the scientists realized this. They got caught up in this enthusiasm. Their curiosity was bubbling over. I think that ultimately is also part of what drove the public response, that the public sensed the scientific excitement. News crews start descending on JPL. You start having all these news vans out in the parking lot. You have the press conferences attended by hundreds of people from the media.
One can have gravitational instabilities where the rings...
Which was something I think that you didn't see previously for a lot of scientific events. I think that's fairly safe to say.
Normally, my experience had been getting press attention and wanting to tell my story. In this case, the press wanted us to tell the story.
They had become, in a sense, kind of space junkies. They liked the space program, they knew about it, and they became, in a sense, almost fans of JPL.
What is the albedo of clean eyes that is not exactly purely clean eyes and not exactly dirty eyes?
2 rows back, please.
Do you have a rough handle on what the orbital period or velocity of a theoretical moon in the Cassini division would be?
In the second row here, there's been a hand up for some time.
We seem to be losing the distinction between small moons and large ring particles. And I'd like to know if anybody is able to come up with a definition now of which is which. Those of us who like to count moons are starting to get worried.
With each encounter, Voyager became better known. And scientists and engineers were more media savvy. Some were even doubling up as news anchors.
This morning, we have Dr. Jay Holberg.
I just got asked. I think JPL was looking for a young female engineer who knew something about the Voyager project and what Voyager was going to do.
Dodd joined the Voyager team right out of college. She had moved up the ranks and was now responsible for the commands that would have Voyager executing a daredevil flyby of Neptune.
And I thought, okay, my career's kind of riding on this one because I built the closest approach sequence, and if it goes wrong, it's my, it could be my fault.
Then the gravitational force of the planet bent the spacecraft downwards towards the final flyby. Scientists who were accustomed to extraordinary sights were still amazed by what they saw at Neptune's moon, Triton.
Last night was certainly a night to be remembered. I think it's the most exciting night that I can remember from any of the encounters that we've had with Voyager, and there have been some exciting nights. Without a question, the images that were returned this morning revealed a world unlike any of the others that we've seen.
These were erupting geysers, shooting out material miles into space. In other places, there were lava-like flows of ice, all of it believed caused by volcanic processes underneath Triton's surface.
A world at the very, very edge of the solar system, frozen, we thought would be completely geologically dead, and it turns out to be geologically active. That was a great surprise.
Once again, it's a moon that steals the show here.
Yeah, I really think of Io and Triton as the bookends for the planetary era of Voyager. I mean, the surprises are at the beginning and even at the end. The temperature there was minus 390 degrees Fahrenheit. Nitrogen is frozen solid in the icy polar cap, and yet a little bit of heat and you get plumes. It's just told us that, in fact, nature is much more capable than we would have imagined given our terracentric view of planets.
You're at the point now where this part of the mission is ending, and when you reflected back on it, what do you think were the biggest takeaways to share with the public about this outer planet exploration?
I think it was just the diversity of bodies in the solar system. I think that's what, they could have all been heavily cratered ancient bodies, but in fact that's not the way it is. And today we know there are other stellar planetary systems, and they're all different than our system. So it just says there, from a science point of view, there's an enormous amount to be learned about planets, moons, rings, and magnetic fields. They were all different and were different than we expected. And we learned a lot, and there's still more to be learned.
And Susie, I'm glad that it went well with your sequence there.
Went well, yeah. I wouldn't be sitting here today if it didn't go well. So, yeah. But it was, you know, Voyager. I think most people who worked on it would say that it's definitely up there as a career highlight for them. It is for me personally, and I just feel so fortunate that I was able to work it at the beginning of my career. And I'm working on the project now. I might make it to the end of my career. I don't know. You know, as I always say, I'd like to get Voyager to 50 years. Please come back in 10 more years. It'll be hard, but Chris will be around, helping me out, remembering what memos he wrote down and things like that. But Voyager is a great mission, and I think most of the people that have worked on it and the ones that are still working on it today feel very fortunate to have been involved with it and to be involved with Dr. Stone. So.
And appreciate your time in front of the media there, being a broadcaster. And I want to talk a little bit about the public and the media. I was reading today in the New York Times an article by one of these reporters who came out here. We live in a different world now, but back then they would come together and became almost like a veterans group that would get together every few years to have these reunions. And for the public itself, I think the Voyager record, John, that I know you were inspired by what the Pioneer mission had done. They'd started that off. But tell us a little bit about why you decided to have something done on this spacecraft that ended up being the Voyager record. That's John, by the way.
Oh yeah, that is John. Well, I remember very clearly the event that happened with Pioneer 10, where Carl and some others had put a plaque. Carl Sagan had put a plaque on the side of the spacecraft that showed the outline, just the outline form of a human, male and female. Naked, but there wasn't any much to see. But they were. So anyhow, but it created such a stir among the public and in the press, and you know the comment with somebody said NASA was sending smut into space and all that kind of stuff. But you know, to me, it represented a real connection between the project and the public. And after all, the public is the people that pay for this, right? Ed always used to say we've got to have missions that are publicly engaging, not just scientifically worthwhile. I remember when I was managing Vision 34, I wasn't on the project yet, but we were providing hardware for the project, and there was some review I was sitting up, and I asked the question, are you guys going to put anything on this spacecraft? And they said, what? What for? I said, well, send a message. And they said, no. But then I got to be project manager. And so remembering the Pioneer thing, Carl Sagan was on the project at that time. And he was a pretty good friend of mine. And so I called him up one day and said, hey, Carl, you know, we need to have something on this spacecraft. Are you willing to take a crack at it? He said, absolutely, yes. He said, give me a proposal. He came back with $25K and 3 or 4 people he was going to put together as a team, and they had sort of a general outline. And I said, good, go ahead with it. And so out of that came the record. And I think the record is tremendous. We had 3 things on that spacecraft that were all messages to 3 different groups of people. One, we got everybody who was working on the project and all their families and significant others. There were 6,000. We had a big a family day. The spacecraft was in the thermal vac chamber. We had tables set up outside where people could write their name. And we had 6,000 signatures, and we photographically reduced them to a little 6x9 aluminum foil, and they went into the thermal blankets. So that was a message, and it was a message to the people that we are acknowledging your contribution by putting your name or your name of your family and friends on it. So that was one. The other one was the American flag. The American flag was acknowledgement to the taxpayers. We recognize you, we recognize this country and the dedication of everybody in the country who supported it as this. And the third message was a message that Carl sent, you know, which was not only a message to the aliens, if there ever were any, but it was also a message he was, I think, trying to stimulate people on the Earth to think about how you would go about communicating with a totally foreign society or a totally alien culture. And there was a lot of that was embedded in the message.
How we define ourselves.
And how we define ourselves, yeah.
I was going to add that as a project manager today, we get lots, and I'm sure Ed does too, we get lots of emails from all over the world, both congratulations about the great science that Voyager does, but also, you know, congratulations that there's this gold record, that there's this time capsule we're sending out there. That really resonates with the general public, and I think that's what makes Voyager so world-renowned and known by everybody.
I like to say that the 2 Voyagers, after they finish their current interstellar mission, will be orbiting the Milky Way galaxy for billions of years, and they'll be Earth's silent ambassadors, and the golden record is sort of the calling card carried by those silent ambassadors. And this is a very inspiring thing for the public at large, it turns out.
Yeah, the spacecraft they'll last longer than our planet and our star, so.
It's just like the final picture of looking back on the solar system. It has absolutely no scientific value, but it is a tremendous significance, you know, of a perspective. And the golden record is the same way. There's no science value in that, but it's a connection to people. You know, underneath it all is the people in this room and the thousands behind them.
That's the great engineering.
Yes, and it's not only engineering, it's commitment and dedication and perseverance. Yes. And I was thinking when you were asking one of the lessons, we had another kind of a mascot motto on Voyager. It was an image, a cartoon image of a bird, I think it was a pelican or something, and in front of the pelican was a frog, and the frog had his front legs around the neck of the pelican, and the pelican had the frog's head in its mouth. And the caption was, "Don't ever give up." And that was a reminder to all of us, you know, but you know, there were the examples of that. The unsticking of the scan platform, it looked like it was over there for a while, but a couple of guys said, no, let's keep working on this. And then the recovery from the failed tracking loop capacitor on one of the radio, you know, where the DSN guys came in with a programmable VCO or something that we could match whatever the receiver was doing from the ground based on, you know, trajectory analysis and everything like that.
Well, we need to move into the next phase of the mission, which is historic also, and the first interstellar object ever in the history of humankind.
Right. Yes, the sun protects all the planets with its solar wind. Million-mile-per-hour wind creates a huge plasma bubble around the sun itself, and the bubble envelops all of the planets we flew by. And we had no idea how big the bubble was. We had an idea, but we didn't have any very accurate. So we didn't know how long it would take to get there. We didn't know how long spacecraft could launch. After all, the space age itself was only 20 years old when Voyager was launched. So there was no empirical evidence that anything could last 30 or 40 years. But in fact, Voyager 1 did leave the solar bubble, the heliosphere, in August of 2012, and is now exploring nearby interstellar space where the material comes from other stars than our sun, and where the magnetic field is the magnetic field of the Milky Way galaxy, which is being wrapped around the outside of the heliospheric bubble. So, and what we've discovered out there is that the cosmic rays, which we measure here on Earth, are more than 4 times more intense outside. We didn't know how many were out, what the radiation environment was like. It could have been hundreds or 1,000 times worse. Turns out it's only 4 times worse than it is here at Earth. And we will be studying that aspect of interstellar space as well in the remaining life that Voyager has with its radioisotope thermoelectric generators.
I'd like to close out by actually having a sense of what it would be like if we were on Voyager and looking back at us. And I always wondered about how could we do that and what would that be. But we now have, thanks to our JPL created eyes on the solar system, a way of looking and seeing where the Voyagers are and looking back. And there you have it. This is available online at Eyes on the Solar System. You can just Google it and there it is. Wave.
Well, you know, I think part of what makes Voyager what it is it's great engineering, it's great science, and it's remarkable inspiration. I think those 3 elements all came together and have made a journey that's really unequaled.
What an inspiration all of you are to all of us. And we just thank you so much, and all of you that have worked on this mission. It is truly of historic proportions, and how privileged and special it is. And with that, I want to thank you for coming and thank our audience. You've been terrific, and sail on Voyager.